When the CPU is powered on or reset signal is received, the PC is always set to 0. It's not the case for every CPU, but for the 8080, 8085 and Z80 it is. So your ROM should always start at the address 0. A quick example: loading accumulator with hex value 12, incrementing register A, and halting the program. So at the memory address 0, there we have the command 3e. It's a 2-byte command. At 0 it's 3e, at 1 it's 12, and at address 2 there is the increment accumulator, and at address 3 is the halt command. By the way, the halt instruction suspends the CPU until a reset or an interrupt is received. So at address 0, there's a command loading accumulator with the value 12. Accumulator is loaded. The next command is at memory address 2, incrementing accumulator. Accumulator is incremented. And the last command is at memory address 3, which is the halt command. To modify the program counter, you can use the command jump, and you specify a memory address. So at memory address, it's a 3-byte command. At memory address 0, you have the jump, and then the address, and it's saved with the low byte first. So 40 is a low byte and 0 is a high byte. Have a look. C3 is the jump, and at memory address 1 is 40, and memory address 2 is 0. So at program counter 0, you will jump to the program, will jump to the code at memory address 40. Program counter is set to 40, and the next command is a no operation command because the memory is 0. The no operation command is just placeholder. It consumes 4 clock cycles, but doesn't change a register or a flag. So at memory address 40, let me specify an operation command, and here a jump back to the halt command is at address 3, back to 3. So here's an operation and the other jump command. We'll jump to 40, we'll execute the no operation, and here it will jump to the address 3. And at the address 3 there is a halt command. In the assembler you don't need to calculate the destination addresses, but you can specify labels. I will name the first label label 1, and here a label stop. Here is label 1, and here I will jump to label stop, and you can see here the assembler is calculating the correct addresses. jump to stop. So this is an unconditional jump. It will always jump. I will show you another unconditional jump. Loading HL with the address of the stop label. And here jumping to memory address in HL. So here you can see E9, it's a one-line command, jump to memory address HL. Loading HL with memory address 03. 03 is loaded, so the program, the command jump HL will jump to the address which is specified in HL. We'll jump to 3, and that's a hold command. It does also work, so it's HL, IX, and IY. But in this case, the jump to memory address in IX is a 2-byte command. IX is specified, and then jumping to 3. And the same goes for IY. Now jump, conditional jump on 0. That means jump only if the 0 flag is 1. So in this example 0 flag is 1, so we will jump to the address 40. If I say here jump on non-zero, he won't jump because the 0 flag is set. You have the following jump commands: 0, non-zero, carry, non-carry, parity even, parity odd, and jump on plus and jump on minus. Load the accumulator with 10 hexadecimal and subtract 11 from it, and here we are doing a jump on minus. So accumulator is loaded, subtract 11 from the accumulator, the result will be negative. So the result is negative, the sign flag is set, and here we'll jump because the sign flag is set. If I subtract only 1 from it, the result is positive, so the sign flag is 0 and he won't jump. Loading 10, subtracting 10, sign flag is 0, which means it's a positive number, so you will jump. If you want just check the value in the accumulator, you can use the command compare. Compare is doing almost the same thing than the sub, with the exception he won't put the result in the accumulator. So he will leave the value in the accumulator, but will set the flags. A is loaded with 10, subtracting 10 from it, but leaving the original value here. But he will set the flag, he will set the 0 flag here. Value is still 10, but the flags have been changed. Will be a negative number, so the sign flag will be set. And it won't jump because it's only jump on plus. And there are also other compare commands. You could say compare with B, A, B, C, D, E, H, L, memory address HL, X plus index, and RY plus index. Removing this line, loading B with 9, A is loaded, B is loaded, 10 minus 9 is 1, so it's a positive number, sign flag will be 0, and he will jump. So specifying the IX register and comparing it with the index minus 3. And here jump on carry, or non-carry. IX is loaded. FF minus 3, 1 through 3, putting 2 here, so 10 minus 2 is 8, and that's a positive number, so the carry flag will be cleared. Carry flag is cleared, and he will jump because it's a jump on non-carry. So 10 minus 20 is a negative number, so the carry flag will be set. Carry flag is set, and he won't jump because the carry flag is set. So what's left? Parity even, parity odd. Let's do an exclusive OR with the accumulator. Commenting this out, and here jump on parity even. Exclusive OR will clear the accumulator. Parity is even because there are 0, 1 bits set, so we will jump to the address 40. And end with the accumulator and jump on parity odd. FF and 1 is 1. Parity flag is 0 because there's 1 bit set. You will jump to the address 40. Parity odd. Next to the compare command, we have also the command cpir, cpi, cpdr, and cpd. But these commands we will see in the next chapter. The Z80 has 5 further jump commands. So the normal command, like here, that's an absolute command. With an absolute jump command, you specify the 16-bit address, destination address. And with a relative jump, you specify only an index. So, for example, you jump, relative jump to test label 1. And here's test label 1. So here's a relative jump command. The index is 0. That means it's just the next command. So for example, if you have here one command between, or even 2, so the index is 2. That's 0, 1, 2. It will jump to the halt here. You jump to the halt, program counter is 4. You can jump forward or backward. So for example, you have here test label 0. And here you jump to test label 0. That's FC, it's a negative number. So here you have FF, FE, FD, FC. So we'll jump to 0. And you jump to 0 again. So next to the relative unconditional jump, you have also a conditional jump, like 0. I mean, like Z flag. Is 0 flag set or not? So you have the following relative jumps: 0, non-zero, carry, and non-carry. There's no parity odd, parity even, or plus or minus relative jump. These jump commands only exist on the Z80. Okay. Let's do a little cleanup here. Well, let's call it here weight. That's a weight label. We are decrementing B, and we're doing a jump on non-zero, comma weight, and jumping back to stop. So B is loaded, is jumping to the address 40, decrementing B, 0 flag is not set, so jump on non-zero, it will jump back to 40, decrement again, so B is now 0, 0 flag is set, and jump on non-zero won't work because 0 flag is set. It will jump to the halt command. So you could replace your absolute jump with relative jump. So the jump is now only 2 bytes long, and it will work the same way. But there's even a shorter way to do it in the Z80. Use the command decrement, jump on non-zero, and to the label wait. So the command here is a 2-byte command, and FE is the index. It's FF, FE. So decrement jump on non-zero will decrement B until B reached 0. But it won't set any flags. So decrement, false decremented, but the flags are not modified. 3, 2, 1, 0. So it will jump back to the halt command. But this command does only work in the Z80. Suppose you want to use the wait command here as a subroutine. So in your program you have some code. Later on you will call the wait command again. So what will happen here? Here you have the first jump. It will jump here to the wait, and after that it will jump to the stop. So there will be no difference between this jump or this jump. For that you have to use another command, and that's a call command. Call wait, call wait, and here you don't do a jump back but a return. Let me first set a stack pointer at address F0. So stack pointer is set, loading B, and now the call command. The call command will jump to the address 40, but before he will put the next address after the call command, in this case address 8, to the stack pointer. So the stack pointer will be decremented by 1. It'll put the high byte of the address and decrement it again and put the low byte. So F0, he will put the address here. So he jumped to the address 40. Stack pointer has the address EE now. That's EE. And here you find the return address. Low byte, high byte. This is address 008. So with the return command will retrieve the address from the stack and jump to that address, in this case to address 8, and he will increment 2 times the stack pointer. Jump to address 8 and the stack pointer is back to F0. The next call command has put the address 000D on the stack. We can also have nested loops. I will just remove this one. And here I will do another call to dummy, and dummy is just an operation and an return. So jump to address 40. Here's a return address. And he jumped to the address 46, where the no operation is. And he has put the return address 045 on the stack. 045. With return, I will jump to the address 45, and then the next return to the address 8, and then the halt. So you can specify a lot of nested jumps or nested calls, but be aware not to overwrite your own code here, because the stack pointer will always decrement with every call, will decrement 2 bytes. Okay. Suppose you want to call the wait subroutine, but use a 16-bit value. So loading the register BC with the value 3000. And here we can't use the decrement jump on non-zero because it works only for the register B and not BC. So we have to write our own subroutine. Let me remove the call here. And a dummy. So we have to decrement BC, and we can't say here jump on non-zero wait, because with the decrement of 16-bit values the flags are not modified. Decrementing BC is decremented, but the flags aren't changed. Yeah, stop now because the 0 flag was already 1, and that's why he stopped. So you could compare every register, B and C, if they are 0. You would do it like this. Do an exclusive OR with the accumulator. Exclusive OR with the accumulator will clear the accumulator, and then compare B to the accumulator, and later on compare C to the accumulator. But that's not an optimized code. It's easier to do it this way. So decrementing BC, that's okay. Then loading the accumulator with register B and do an OR with register C. That's all. So decrementing BC is decremented, loading B to A. So B is transferred or copied to A, and we will do an OR with C. As long as A and C is not 0, the 0 flag will not be set. So 0 flag is 0, and he will jump again. He will decrement it. Okay. He'll decrement it until BC is 0, then the 0 flag is 1. Zero flag is 1, and that made him stop the program. Maybe you ask yourself if there is also a conditional call command. Yes, there is. For example, call only when the Z flag is 1. So Z flag, non-Z flag, carry, non-carry, parity odd, parity even, on plus and on minus. The same goes for the return command. You could say return on 0, 0, non-0, carry, non-carry, parity odd, parity even, on plus and on minus. So here he will only return if the 0 flag is set. I hope you enjoyed the video. See you in the next part. Bye bye.